Okay, welcome everyone. It's my great pleasure to introduce Dakin, who today is going to probably straddle both a computational science talk and an astrophysics talk. So I think we get both for the same price, so to speak. Anyway, Jeppe, I got to first know when he did part of his PhD at the University of Zurich. He visited us for 2 months, and he was very instrumental in implementing the treatment of neutrinos and gravitational gauge in the GR gauge and into the code of our code, PKD graph 3. And without him, I don't think we would be able to do the simulations we now can do with PKD graph 3. We borrowed a lot of ideas from his own code, which he developed during his PhD concept, which can handle neutrinos at the nonlinear level as well. And he then went on to do his 2 postdocs, I think, at Aarhus, where he also did his PhD. And now he has been awarded the Tomala Fellowship and is here on a postdoc in Zurich again. I'm very happy to have him back. So I'll give you the floor. Yeah.
Hey, thanks a lot, Joachim. Yeah, and welcome to my talk about my n-body code concept. So concept is a code for simulating cosmic structure formation. So this involves primarily, let's see if this works. Yes, amazing technology. N-body techniques, but on top of that, it also implements a lot of extra fancy stuff like general relativistic corrections. And here I just put exotic species like neutrinos, for example. Right, and together, these 2 extra things make the simulations consistent with linear perturbation theory. So not only can we do nonlinear stuff at the low scale, but we can also still be consistent at the large scales where GR is important. Right, and so the output of such an n-body simulation is just a bunch of particles, and that's hard to compare to other simulations, but also to the real world. So we need somehow to extract some statistics from these particles, and Concept can do this as well, using 2 statistics, the power spectrum and the bispectrum. Yes, so here's just a nice plot of a bispectrum. And the code is open source, available on GitHub. And the code is now 8 years old since I started developing it. So it's getting mature, you could say. And thanks. Yeah, so it contains a lot of different stuff. And I thought about what should I talk about today? Should I deep dive into one particular thing? But I thought, no, let's make it less technical, but much broader. So I'll go through the majority of things the code can do, but that also means that I don't get to go as deep into the stuff as I could. So you'll get a broad overview of lots of different things today. Right, and though I'm the main developer of the code, I of course could not have done this alone. So throughout these years, the main collaborators has been Sten Hannestad and Thomas Tram, both from Aarhus University. Okay, so let's dive into computational cosmology. So if you imagining a cosmic timeline here, wrong button, this one. Timeline, pick your favorite cosmic time parameter. Then at early times, the structure in the universe is linear, and we can solve it using so-called Einstein-Boltzmann codes, where class is the most common, I think, but definitely the most modern one. But then at some point, the matter in the universe goes nonlinear, and we need to simulate it using n-body techniques, where concept is one possibility. So what's the difference between these 2 types of codes? So the Einstein-Boltzmann codes are really just a large system of ODEs, which I've tried to depict using this coupled system of differential equations here. Whereas the simulation codes, n-body codes, well, they still solve equations, but not as directly. They actually have a set of particles which we track through space, which is very, very different. Okay, and we could, if we wanted, add another sort of computational era to the universe, namely inflation, which seeds the structure and give rise to the initial conditions for the next stages. But I will not go much into inflation in this talk. Okay, so let's start developing a basic n-body code. So first we have a box with n particles. Here n is 4. And we want space to be infinite, and we simulate that by having the box be periodic. So whenever a particle goes through a boundary, it just appears at the opposite end. That's fine. Then we add gravity. So here's the gravitational force on particle I. It's the usual 1 over r squared. Here x, but I tend to say r, whatever, 1 over r squared. But this now is complicated because the box is periodic. So the force also goes through the box periodically. So each particle exists an infinite number of times throughout space. Here I've just drawn the nearest neighbor images. And this means that the force on any given particle really consists of an infinite number of forces from each other particle. So this expression has to be modified by an additional infinite sum over all these images of the box in 3 dimensions. And this is not easy to compute because this sum doesn't really converge nicely. So the usual trick is to make it seemingly worse by writing this sum as now 2 infinite sums, 1 over, I call it n and h, but never mind. And this is better because these sums both converges exponentially, meaning that instead of doing it over all 3 tuples, we can cut the summation quite early and get the right answer. Right, and these two parts are called the short range and the long range force. So here I plotted the force. So the blue line is the total periodic force, which is the sum of the green and the orange ones. Right, so at low separations between particles, the short range is pretty much all there is. And and then also the black one is a normal non-periodic 1 over r squared force, which is the same at short distances, but at longer separations, the periodic nature of the force comes into play, right? Okay. So this is one basic way of doing this gravitation. So here I've animated how this looks, and it looks sort of okay, but sometimes 2 particles get a huge boost in velocity, which is non-physical due to close encounters. So energy is not conserved if you just do this. It's just because 2 particles can get close to each other, and the 1 over r squared force diverges, right? So we need to somehow so-called soften this force. The way to do this, let's see, is to remove the 1 over r squared divergence and then add it back in a softened version. So here this symbol goes down here. So instead of 1 over r squared, we have this extra cubed here. We have this extra epsilon, which means that when you put it in 0 here, this term doesn't diverge. And if you're clever about this, epsilon is not a constant, but some function of separation, so you can have a nice, smooth softening. Right, and so this new box here is with the softening, and now you can actually get nice simulations where you see small halos forming. And this is actually the most precise in-body simulation you can have, but it's very slow. So it's called PP for particle-particle. You just pair every particle with every other particle. It's very precise, but it's super slow. So most work in in-body codes try to take this and make it much faster through various magic. Okay, one way of doing this is to, instead of having direct forces between particles, you introduce a mesh where you solve the potential instead. So here's the Poisson equation for the potential, given in terms of the density field. Now you need to solve for phi, which is hard in real space, but in Fourier space it's quite easy. Okay. Now we need to take the particles and somehow interpolate them onto the grid points. So here this W function is some interpolation kernel which maps the particles to the mesh positions. Okay, then we got a grid of density values. Then we can go to Fourier space and we can divide by k squared to now get the potential instead. Then we can go back to real space to get the potential. Then we can differentiate it using some differential operator to get the force, again, still on a mesh. And lastly, we can interpolate the forces back to the particle positions to get any given force on a particle. And then we are done. Yes. Okay, so now the question is how to do this interpolation functions, the W's, and how to differentiate the D. And there's various different ways you could do this. So constant influence, this doesn't mean anything to some people, but anyway, it's some well-known ways to interpolate. And Concept has them all. You can choose. And how to differentiate, you can use different orders. So doing it with the 2 here means take the 2 neighbors and do the simple stuff. And 4 means take 4 neighbors and so on. And Fourier means do the differentiation in Fourier space. So move this in here before you go back to real space, which is more precise, but also more expensive. You can pick and choose, which is nice. Right. And then on top of this, there also comes the fact that we can deconvolve the potential, which is just some way of correcting for the interpolation. And we can also use interlacing, which is another way to do this more precise, but it's much more costly as well. Okay. And yeah, the main point of this thing is that it has n log n complexity. So it's much faster than n squared. But the downside is that there's now a mesh, there's a finite scale at which you can resolve gravity. So anything below that, you miss out on. So on small scales, you don't get the correct behavior anymore. Okay, but let's say that we are now happy with the gravity. So we can now do an n-body simulation. If we also have time stepping, which I won't go over now, and also some way to initialize the particle configuration. So in the end, we get something like this, a bunch of particles. Now we need to extract the statistics. So how do we do this? So one way to do this is to convert. You can map a bunch of particles to a hierarchy of so-called polyspectra, which goes like this. And the top one is the power spectrum, which is the one most used. So here I've written it in a sort of weird way, just to give the same structure as all the other ones. But this can be reduced to this nicer form. So the power spectrum is just some function of k, which is just the density field in 3 dimensions in Fourier space, squared, and then average over all directions. That's quite easy to compute. And if you do this, then you convert this bunch of particles into a plot like this, where now the blue line is the simulated power spectrum, and the black line is the linear one from class, for example. So at large scales, they agree pretty well, but then at some point, the universe goes nonlinear, and we want to capture this nonlinearity, which is the whole point of these codes. Okay, fine. Now, how do we start the simulations? How do we make the initial conditions? Basically, we just take this scheme down here and we reverse it. So we want to go from a power spectrum to a density field. So basically, I just now solved for delta, and you get this, where R is some field in 3 dimensions, which has this mean value of 1, and P is a power spectrum. Right. So this R, we have to choose this R in some manner. And from inflation theory, we know that, well, at least most models predict this R to be Gaussian at early times. So you just draw some random Gaussian numbers, and you have this starting field. Now this power spectrum in here, we cannot use the simulation power spectrum, obviously, because we don't have that yet. But at early times, we can use the linear one from class, which is just the product of a transfer function and a thing called zeta. So now here, this new plot here is the transfer function of density field from class times this random field. And now the last ingredient is this zeta, the primordial curvature perturbation, which also is a thing you get from inflation. And now add this as well, and you get something which looks like a nice field to start out with. So this is the total delta at early times. Right. So this is how we make the starting conditions. But you may ask, okay, that's fine. So now you have some field with the right power spectrum, but what about the higher order spectra as well? But again, from inflation, most models predict that at very early times, you only have Gaussian perturbations, meaning that this hierarchy is cut off here. So all the other higher spectra, they vanished at early times. So we don't need to care about them. Almost, at least. So fine. Now we have power spectra as well. Now let's move on to the more fancy stuff, the non-matter parts. So here is another timeline of the universe, now with a second axis, which splits the physics into Newtonian physics and relativistic physics. So if you track the particles through the universe's history, we see that matter, so here matter means baryons and cold dark matter, they start out being linear and in a relativistic setting. But then as time goes on, they become nonlinear, but also Newtonian, meaning that we can solve everything using Einstein-Boltzmann codes and n-body codes. We never need to go up here doing nonlinear GR, which is not obvious, but our universe doesn't need that for cosmology, which is nice. It makes things easier. We also have photons, which remain linear throughout the history of the universe. And we have neutrinos, which also remain linear, more or less, throughout the universe. Okay, so let's try now to incorporate these linear species, the photons and the neutrinos. So here's my personification of the class code and another timeline. So we use class to set up the initial conditions for the matter particles. And then we solve it using this PM scheme to get the gravity. So here we compute the potential, and that gives us forces back to the particles. And we use this to propagate through time. Now we also use class to create a density field, the total density field of the photons and the neutrinos, and use this as a source of this field as well. So through this field, the photons and the neutrinos now interact or gives a little kick to the particles. There's a one-way force, but that's fine. And at each time step, we now do this realization down here anew. So at each time step, class creates a new field down here, and we use this to perturb the total potential and use this to incorporate their little gravity equations for the particles. Okay, so let's see if that actually works in practice. This is a somewhat busy plot. Let's try to make sense of it. So the colored lines are, first of all, the whole thing is the ratio of two power spectra from two different cosmologies, one with a massive neutrino and one with a massless neutrino. And the ratio is just nice because then you can see small errors better than the absolute scale. Okay, so if you look at large K, meaning small scales, we have some nonlinear behavior, which is not seen in the black line, which is the linear class results. So this is the normal in-body thing that we want to extract. But now we also want to be consistent with class at early times, but also at large scales. So if we track the purple dashed line and the full purple line, they deviate around here. And the dashed line is just a pure matter simulation, a normal in-body simulation. But now the full line is where we add this neutrino and photon corrections in. And this actually makes it follow the relativistic behavior much more closely, which is nice. Now we get the correct behavior at both ends, the linear stuff here and the nonlinear stuff here. And it doesn't quite work if you look closely. For example, the green line here doesn't quite match the black line over here. There's still something that is missing. And it turns out, of course, in GR, not only the density gravitates, but also the pressure and the momentum and the shear. So we need to add this missing gravity from all the species in as well. And there's a super neat, almost a hack way to do this. It turns out that, at least in the so-called n-body gauge, there exists some fictitious density field whose Newtonian gravity implements exactly the GR gravity that is missing. So we can construct this weird-looking density field, which doesn't correspond to any real species, and add this in to our collection of linear species. And this exactly implements the missing GR gravity from all species. And if we do this, the green line and the orange line pops back in where they should be. This is super nice. This is what is also in the PKD graph code now. Right. And now with this scheme, we can go crazy and add more funky exotic species. So for example, dark energy perturbations. So if you replace the lambda with some funky dark energy without perturbations, you can do this as well. There's a similar kind of plot as before, the ratio between two power spectra, one with some fancy dark energy, which has a equation of state not equal to -1, divided by the normal lambda dark energy. And this has a similar story here, really. Nonlinear behavior here, normal Newtonian behavior here, but then if you add in the extra species, you can make it fit the linear results nicely.
The species that contribute to the effective gravity.
Yes. It doesn't really matter. It is, yes, but it doesn't matter. So here, so this is, so when I write sigma here, for example, this is the total shear of all particles, but the contribution from matter is 0. Matter has no sigma, so it doesn't matter. The same for the pressure, not the same for velocity, but it's multiplied by the pressure. So it doesn't matter in the end how you do it. Right. Okay. Now the neutrinos, as Joachim also mentioned, these guys have some mass which we don't really know because you just play around with it for fun. If the mass is high enough, they go sort of nonlinear before the present day, and we might want to capture this effect as well. Right. So back to this scheme. Now we take the neutrinos and we separate them out into their own species. So now nothing new has happened. We just have the photons and this metric here, and the neutrinos by itself down here. Same as before, really. But now we can add in the neutrino, not density field, but the momentum field, or the velocity if you want. This is a vector, so there's now 3 scalar fields. And then we can solve for this density field of the neutrinos non-linearly within concept using the continuity equation. Now this density field still affects the global potential, but now the potential also goes back in and affects the velocities of the neutrinos. So we need the Euler equation now to solve for the velocities, and this Euler equation for neutrinos and basically all other species than matter contains higher order moments, such as this pressure and the shear. So we also need all of these scalar fields now to update the velocities properly. And this goes on forever, really, but we need to stop somewhere. So in concept, we stop here. And now these guys are still realized through class at every time step, while the 4 here are evolved non-linearly inside the code. This is a way to make it, it's sort of a mixture between linear and non-linear computation, because, well, some moments are non-linear, but others are linear. And the total effect is fine as long as these really are linear at all times. And that's the case, at least for standard model neutrino masses. Okay, so just a quick plot. Here's now the neutrino power spectrum, just the absolute spectrum, for 3 different masses, the linear and non-linear results. So actually, you can get what is this, factor of 100 or so more power, which is a big factor, if you do this non-linear thing. So you might think this is very, very important, that we should always do this. So here's a nice sort of plot of the neutrino density field of I think a 0.1 EV neutrino computed linearly. And now this is non-linearly. So you can see that if you add this nonlinear correction, they sort of cluster much more nicely, much more compactly. And now here I've added in the matter. So now the white filaments are matter, and all the purple stuff is still neutrinos. And you can see when we go back and forth between the linear and nonlinear neutrinos, they follow matter much more closely here, but the matter itself doesn't really budge. So if what you're interested in the end is the matter field, how you do the neutrinos doesn't matter much, really. But if you are interested in the neutrinos themselves, you need to take this nonlinear behavior into account. Right, and this whole scheme is used mostly for neutrinos, but you can also use it for any other species. It's totally generic. So people are using it also for warm dark matter, for example. It's the same thing exactly. Okay, let's now go to yet another species we can have. Decaying cold dark matter. The basic process is now we have some decaying cold dark matter, which decays into some dark radiation or decay radiation. No one seems to know which one is correct, so we just say DR. Okay, so a new matter species, which is decaying, and another sort of radiation species. And just to be clear, this is some photon-like species, but it's not the photon, because then we would have seen it. Just imagine some new photon-like species which doesn't interact electromagnetically at all. Okay, let's try to make this work as well. So our matter species now consist of baryon, cold dark matter, and decaying cold dark matter. And how do we make these things decay? We take the particle mass and we let it drop through this decay rate gamma, so e to the minus gamma t. That's sort of simple, but because one n-body particle really corresponds to both baryons and cold dark matter and decaying cold dark matter, only one of the guys are decaying. So how does the total mass now go? Really, it's not so obvious. But we can. So the real decay rate of the decaying cold dark matter is this guy, and we can weight this in this fashion to make a new decay rate for the n-body particle. And this decay rate is time dependent, so it's a bit funky, but it checks out. Okay, so now the mass goes down, at least initially, until the decaying dark matter is gone. And we also add this decay radiation to the linear species down here. And we should be good, one might think. So here's a similar plot as always, the ratio between two power spectra, one with decaying dark matter, one without decaying dark matter. And I've chosen half of the cold dark matter to be decaying, and here there's some decay rate. It's not super important. And again, if you just do the normal matter, we get the fine behavior over here, but we don't hit class at the large scales. Then we can add in the linear species, and it works nicer, but it's not quite right, really. So this arrow means all of the above plus these things. Okay, so what we are missing is that if we check the continuity equation of normal cold dark matter, there's a nice zero here, at least in n-body gauge. But if you go to the decaying cold dark matter, there's a term here, which you can think of as a time dilation. So currently, the mass of each particle just drops down homogeneously, but each particle should have its own clock sitting at it, and it should be affected by the local potential, really. And this, at first, seems very hard to implement, but we can just use the exact same trick as with the metric. Now we just invent a new species called the lapse species, whose Newtonian gravity implements this time dilation. It's super magical that you can do this, but you can. With one slight fun key thing, instead of the force being proportional to the mass, it's like the mass is the charge of gravity or whatever. The charge here is proportional to this decay rate. So each particle is now kicked through this extra field down here with a charge given by this thing. And if you do this, you exactly implement this time dilation. Right. But actually now you overshoot a bit. That's because there's a final thing we need to incorporate, and that is collecting these three matter species into one is not really allowed, or it is. But then you get an additional term in one of the evolution equations, which we don't have. And then the easiest way to do this properly is just to have two different matter species in your simulation. You have stable matter and decaying matter, so two sets of particles at the same time. And if you do this, then you hit class exactly. Right.
You do two different species in your simulation.
Yes.
So that doubles the number, right?
Yes. Then you can half. Well, you cannot. You can divide the particle number by 8 or something. But yes. Yes.
So for this decaying dark matter, you have a separate set.
Yes. I mean, you can choose, but if you want to be precise at large scales, yes.
Then at some point they disappear. When
if gamma is very big, they disappear. I guess they don't disappear. They just approach zero rapidly, and then I guess the evolution goes wrong. But now their effect is zero anyway, so it doesn't matter. I suppose I haven't checked the case where they disappear completely. Okay, so just as side note on this, the realization of the dark radiation. So it's the same formula as before. The dark radiation is just given by the power spectrum and this random field. But here's an alternative which we might use instead. So the dark radiation is produced throughout time, and it's supposed to be emitted by the decaying dark matter particles. So having them placed in 3 dimensions using this static primordial field is not maybe so good. Maybe we should instead place them at the positions of the decaying cold dark matter. And we can do this by this prescription. So here we replace R by this field divided by the square root of its power spectrum. And we still have the same dark radiation power spectrum down here. So it's not maybe so obvious, but here's a plot of these 2 strategies. So on top we have the old school decay radiation, how it evolves, and down here we have this newer way of doing it, and in the middle we have the matter. So doing it this newer way, we see that it much more closely matches. It tracks by construction the matter in the universe, which is nice, and yet it's still a linear thing. The power spectrum of this plot and this plot is the same, which is hard to believe actually, but it really is. We only changed the 3-dimensional structure, the placement in the universe. And whether or not this is important is unknown. I sent a hack doing this to a group at MIT 2 weeks back, and they are working on it. So might be some interesting things coming from this. Yes. The entropy? I guess. Yes, and why? How does that affect the system?
Well, it happens very no, I think these simulations start at very late. Right, so that assuming that nothing decays beforehand.
Well, let's say I initialize a simulation at redshift of 100 or something. But all the linear, all these effects at earlier times are taken into account using class. So as long as we can just keep it sort of simple at late times, it should be good. I don't know. Julian? Yes. Photons cluster as well. Just photons cluster as well. Just not as much. Well, the top plot is the same as you would get for photons, really. Yes. But this is not the effect of cluster. The button is not clustering as much as just being. So it fades away like 1/r to the 4th, right? But it's also created. Maybe it's created faster than it is washed away. So in that sense, it should be. Right. Yeah. Okay. So you like the old approach better in that case. It's hard to say. Maybe some mixture is the better way of doing it. It's hard to say. But anyway, if your scales are large enough, I think these 2 approaches go to the same thing. So it's hard to say at some given scale what's the best thing to do. Anyway, some guys are looking into it. Okay, let's now we're done with all the fancy species. Let's return to gravity for a moment. So we're now pretty confident that we can get the large scale things correct, including GR stuff. But now the smaller scales, are they really correct? So far we're using this particle mesh scheme. And if you compare to the old PP scheme, we see that no, actually there's the fact that we have this mesh means that we are lacking some clustering. We can correct for this by using not the PP, but the P3M gravity solver instead, which is a mixture of PM and PP, hence the name. It gives the same results as PP, but it's sort of in between PM and PP in its speed. So it's a nice trade-off. So let's just go through this sort of quickly. So here's the old PM scheme. So again, interpolation onto a grid. solve the potential, go back to real space, get the forces, go back to the particles, and you have the force. Now, this 1 over k squared, we can replace that by this thing, which you might possibly remember from the old eval force from the slide 1 or whatever, meaning that this is now only the long range part, so the bottom sum of the two infinite sums I had before. Then we're missing the short range part, which we can add in afterwards. Now we have the potential up here and direct forces down here. But because these are short range, this sum is not infinite anymore. It's only over the sort of nearby vicinity of each particle, because the force drops off after a certain distance. And this distance is called xr here. Okay, so now the force has two contributions, a long range force using a mesh, that's n log n, and a direct force, that's order n. So combined, it's still an n log n force computation. Yes, yeah, there is, but that's fine. So each a nearby particle contributes, well, two nearby particles contribute with a short range force and a long range force. But from the very first plot, I think, was the orange and the green curve, and they have to both be there to add to the total force. So individually, they're not the correct force, but when you combine them, they are. Okay, so we now need to implement this looping over nearby neighbors in an efficient manner. So this plot is super busy, and I won't mention most of it, but just very briefly, the simulation box now in 2D is the whole thing, and each CPU core gets designated one specific chunk of this box, which we call a domain. And now each domain is divided into a bunch of so-called tiles, which have a size of at most this xr. So that means that if we take this, so this is supposed to be one particle, the yellow particle, if we situated that up here, we know that this short range force from this guy can only happen between particles in its own tile or in its 8 neighbor tiles, because the tile over here is more than xr away. So by doing this tiling, we can efficiently ask each particle to get all its nearby neighbors. And we can do this even more quickly by further dividing up each tile into subtiles. So each domain gets to choose its own subtiling. It also gets to be chosen at each time step anew. So if there's many particles, you might want a finer subtiling. So for example, the red particle here, it only needs to ask about particles in this not quite square regime, this the red hatched region. So by making the subtiling finer and finer, we can sort of approach a spherical region to ask about nearby neighbors. And this speeds up the computation hugely. Okay, fine. We still need to discuss how to go through time. So we have gravity under control, but we also need time stepping. So if we take the box and sort of think of the particles as having two attributes, they have a position x and a momentum q. So we start out at some time, and now we need to evolve both of these attributes through time. And the standard way of doing it is to take a so-called half kick. So we evolve the momentum through half a time step. So it's now not synchronized anymore with the positions. Then we do a whole so-called drift with the position. So they go past the momenta. And then we keep on doing this sort of dance, which is called leapfrogging. And then we're done. So that's a basic. Every embody code does it like this, more or less, and it's very nice. But now, because we have this short range forces, some particles are in clustered regions and need a smaller a bigger acceleration, and thus a smaller time scale or time step than other particles. So we really need to have different time steps for each particle, but we still want it to be this leapfrogging scheme. So how do we do this? So now we still have all the positions down here, but now I'll split the momentum up into 3 different so-called rungs. So when you go down here, the rung number goes up, meaning that its time step goes down. So we still now start by doing this half a step for each different rung. So now some particles are now further ahead than others with regards to their momentum, but they all half a step beyond the positions. And now we do this scheme, which you can animate using this nice clock over here. Now the time is blue. Everything is at a blue position. Then we go to yellow. So we leapfrog down here and leapfrog down here to yellow. And these two stays because there's a yellow dot at these positions. Then we go to green, leapfrog, and now we leapfrog with both of these queues, which is totally symmetric, right? Started half a step behind, now they both half a step in front. Then we go to red, leapfrog, leapfrog, and back to blue, leapfrog, and now the whole system can leapfrog forwards. This is a nice hierarchical way of doing this thing, and you can just add more rungs down here, and it works very nicely. Okay, that was time stepping done very quickly. Let's see if the X actually agrees. So concept, does it agree with other simulation codes? So yeah, I have a bunch of power spectra at different times compared to the Gadget 2 code. And at least at this absolute scale, it looks like it works very nicely. But of course, we need to take the ratio of power spectra to really see the details. So here blue is sort of early time and pink is today. And this is the ratio of power spectra. So we see at early times, the relative difference between concept and Gadget is about 1 per mil at all scales, which is rather amazing. So all these different curves, never mind, it's just different. You can run Gadget in different setups and they give slightly different results. Right. Yes. And then at the later times, the error grows to about 1%, but that's still really good. So it actually works, which is nice. Yes.
So this comparison here, because your code is coupled to that.
Yes.
Gadget.
Right. Yes. Good. So here I run concept without any of the fancy features, just a pure matter thing, which should then match the old school way. Except that you also need to now run concept in not in the n-body gauge, but in the backscaled whatever method. But you can also do that. So you can pick and choose how to do things. But yes, yeah. Otherwise, this error would be much larger. Yes. Okay, so it gives the right result, at least if we trust Gadget, but we do. But how does it actually perform? So you can make all sorts of weak scaling, strong scaling plots, but that's nice. It scales as it should. But another more interesting plot is this plot. So how does the computation time scale as the resolution goes up? So here you can think of it about the Nyquist scale or the box size given some number of particles. So here orange is concept. So concept is much faster than Gadget if you have a large box. So basically concept was developed originally for these large boxes where you have these GR things going on. And that's very fast. But then if you get to very clustered regimes, the P3M method sort of lags behind because there's no tree, unlike in Gadget or in PKD graph. So if you have very clustered situations, the code is really slow. So basically, if your Nyquist scale is 5 or below, you can win a lot by switching Gadget out with concept. But if you are in this regime, you should not use concept. Then you'll have a bad time, basically. And now there's 2 orange curves. The solid one is the actual correct one. But one other reason for concept being slow at these scales is that there's no attempt at all done for load balancing. So if you have a very clustered situation, maybe one CPU domain has the majority of the particles and it does all the work, and the other CPU cores just sleep. That's bad. So, but anyway, we can measure this effect and correct for it, compute another curve, how concept would scale if we were to implement a perfect load balancer. But even here, it's still slower than Gadget, or indeed PKD graph. So this comparison is done with Gadget 2, meaning the old 3PM code. You might ask, what about newer, fancier methods, such as the fast multiple method, which is in Gadget 4 or indeed PKD graph? And I would love to add another line, but I haven't done it. Joachim seems to believe that PKD graph will win over concept at all scales. I'm not so sure. We should find out. Okay, right. So now we have both small and large scales under control, at least when it comes to the power spectrum, right? But what about all these other spectra, which I briefly mentioned in the beginning, such as the bispectrum? We don't really know. but we can just you can try it out. So here's not a simulation, just an initial condition, clues and concept. And then I measure the bispectrum. Here's the equilateral bispectrum, and here's the Q, is the reduced bispectrum. It's just some other measure of the same thing. And the blue line is the thing I get, and the dashed line is what you could compute from theory, from the so-called tree level, perturbation theory at tree level. And it doesn't quite match, which is sad. But you can then do this. It's a very new thing. I don't really get why it works as well as it does. Hence this this crazy markup here. I hope to make a small paper about this in the near future. But if you just upgrade your 1 LPT, which is the name for the normal Saldovich scheme, if you put in 2 LPT instead, which is a well-trod old method, this bispectrum just pops up to the correct level for some reason. I don't really understand why, but it's magical. And at the same time, the old power spectrum is not affected by this almost at all, which is nice. So you have a new sort of spectrum you can correct for, and the old thing stays put, which is very nice. Right. So these bispectrum measurements, we would like to also be able to do them inside of concept. So here's the definition of the bispectrum. You take 3 delta fields in Fourier space, average them together over all angles, set them equal to a bispectrum, but only in the case where the 3 vectors add to a closed triangle. And now you isolate B, which is very non-trivial, but some guy did it. And here's one way of doing it. So for a given bispectrum value, you pick 3 of these k values, which now we are in Fourier space. I picked 3 different k vectors, but only the size really matters. So it turns into 3 rings or shells in 3 dimensions. And then we take the full delta field. So now written it with an index, because this is sort of math. This is numerics. So this is finite grids instead. But anyway, take the delta grid, multiply it by some weight, which is either 0 or 1, depending on whether it's inside the shell labeled by kn. So yeah, I colored it for the green one, for example, the third vector. W is 0 at all points except the green ones. That it's a 1 here, 1 here, 1 here, so on. So you get this weird isolated ring in Fourier space. Then you go to real space, do this for all 3 shells, and you multiply them together, and then you add over all grid cells. It's a really weird prescription. And you divide by the same thing where you forget about the actual delta field. And that's the bispectrum. Right. So this is the way everybody does the bispectrum. But in concept, we went one step further. So now these W's, the weights are no longer 0 or 1, but anything in between. To get these nice anti-aliased smooth shells, which means that the bispectrum value is also more smooth and nice. And again, I hope to make a paper about this very shortly. Right, that's it for physics. Now in the end, I'll just briefly discuss some funky software aspects of the code. So concept stands for cosmological n-body code in Python. It's the first such code in Python, and Python is very slow, but nevertheless, I didn't want to write C for 8 years, so I stick with it. So I just develop here, run it through Python, and it works fine, but it's slow. The normal way of doing this, that everybody else does, is to write your code in C, compile it, and execute it, and now it goes fast. There's also this third way, writing in Cython, which is a funky language, which is sort of a mixture of Python and C. Then you can transpile it to C and to an executable, and then run it through Python and then on your hardware. So this is as fast as C, but it's someone would say this is a nicer language than C. But the real problem is I can no longer just run it directly. What I want is to be able to write it in that sort of nice modern language, and then develop quickly, just run it as an interpreted language. And then when I want the speed, I can compile it. But this is not really possible with Cython. And so to fix this, concept contains a custom transpiler. So I actually do write everything in Python and develop like this. And then when I want to run it, I transpile it to Python, and then to C, and then to machine code, right? Which is sort of funky. And the speed up is about a factor of 1,000, which sounds very impressive, but it's also a bit misleading, because if you had a pure Python code using NumPy and so on, the speed up would be not nearly as big. But this is written in a way so that such as this path is fast, and as a consequence, the pure Python path suffers. So the factor 1,000 is a bit, it's true, but it's misleading. Okay, and I couldn't give a code talk without just some code. So here's just a brief example of some magic that my transpiler does. So here's some code that does the power spectrum computation. So I have some magic Fourier loop iterator implemented up here, meaning loop over all of Fourier space in a sparse manner, whatever that means. Give me the k squared and extract the real imaginary part of the delta field, add them together in a squared way, and you get the power spectrum. Fine. Now this iterator up here is just some loopy code, runs over X, Y, and Z. Yeah, and then there's this sparse flag, which means depending on whether this is true or false, you hit different grid points. Details are not important. But now writing this code in Python is natural. Doing it in C is close to impossible. Writing in Python is also not very fast. But now my transpiler, so this Python iterator decorator up here, it's not a real Python thing. It's something that I added to Python. So now the first thing my transpiler does is to inline everything. So this code block, this Fourier loop gets copied from over here down here. So now I just have the actual code up here, and sparse was true, so sparse is true. Fine. But now we have this weird sparse equals true if sparse. That's sort of not necessary. The next step is to do branch pruning, so it eliminates the branch. And now finally I have these funky symbols here. So this expression, ky bigger than 0, this b means this is some Boolean expression. Please compute this as early up in the code as you can. And the same here, but these c's means integers. So again, replace ky squared by some temporary variable and compute that all the way up here. That's the last step that it does. So it emits these temporary variables automatically. So I don't have to do this manually. That's just some of the weird things that this transpiler does, which is not necessary, but it's fun. I like it. And then Python takes over, and you cannot read this code at all. But you just close your eyes and hope that it works, and it often does. Okay. And now finally, I spent a long time making the code actually sort of user-friendly. So it depends on various things like MPI and GSL and Python and so on. But you just run this magical bash script. This is my 10,000 line bash script, and it installs everything on any Linux system. I'm almost guarantee. And it takes between 1 and 5 hours. It'll get there. Yes, I also have Docker images. If you don't want to install it, you can just run it through Docker. It has a big documentation site, so you can read all about how to do these decaying dark matter simulations or whatever. Right. Oh, and then in the end, it has quite a few fun and someone would say unnecessary features. I'll just end by showing one. There, animation of the evolution in the terminal. Right. So yeah, that's all I have. Thanks for listening. The mismatch at what level? Large scales? Yeah, so class doesn't do this weird thing that it doesn't make this metric species. It just computes GR the proper normal way. Yes. Yeah. So class includes all species that you put into class, and then it does the full GR thing at linear level. Yes. Ah, good. No. If you do that, then the backscaling becomes very non-trivial. So I tend to just run one class up to some point in time, and then just take over directly. No funky business at all. And that works as long as the gauge you do it in is a gauge that how to say it. So this metric species only really exists in a very few gauges, and the so-called in-body gauge is the one I use for it. So as long as you do everything within this specific gauge, which actually perturbs the particles and so on a little bit, then you can just run class and take over directly. No backscaling required. It's much easier, right? The backscaling is a weird hack. Just forget about it. Just run class, and then at some redshift, you just dump it into particles, and that's fine. And everything is in class. You just have to bring over as well. So photons and neutrinos, just bring them over as well. It's conceptually easier than the backscaling thing. Julian?
Yeah, I was wondering about the bispectral study that you quickly discussed, because you said you are surprised that
Yes.
Yes. I think that's exactly how you calculate the theory.
So my 2LPT here doesn't. Yeah, so you the way you ought to do this is to take some initial bispectrum and make sure that your realization matches this one, right? But my 2LPT is very simple, maybe sort of old-fashioned. My 2LPT is computed out of the 1LPT source terms. Nothing new goes into it. I just take the Seldovich fields and multiply them together in some seemingly random construction, and this gives me the second order potential. I don't use any high order theory to get this.
So what's the difference between the tree-level calculation?
I don't even know. I don't know how the tree-level thing is done, actually. I guess they use some second order Newtonian theory, I would assume. Yes. Okay, you would expect it to work without any. Yeah. Okay, good. I can say if you do this is for the equilateral bispectrum. If you do any order configuration, any other configuration like isosceles, it doesn't really work as nicely. And also at later times or at smaller scales, it also doesn't really work. But that might be because you need loop corrections or whatnot. I don't know. Yeah. But you would assume that if 2LPT just matches the tree level by construction, they should at least follow each other, but they do not actually. So there's something special about this equilateral configuration, and I don't know what it is. I don't know. I haven't done this computation myself. It's a way to theoretically predict the bispectrum. So it's not linear theory. I think it's second order theory, and tree level is the lowest possible order you can do to compute the bispectrum, and then you can add on these loop corrections, so-called, to get it more precise. So tree level is just the lowest order theoretical prediction of the bispectrum. Yeah, it seems scale independent, at least for equilateral. I don't know why. I also don't know why there's so to me, the blue line should be 0 really, because I said in the talk that I want to have a power spectrum as the starting condition, and every higher order spectra should just be 0 by construction or by. Yes, but it's not. The blue line is some artifact of the numerics which I'm not in control over. Anyway, I don't really understand this. It's very, very new. I want to dig into it.
Question on the first part. So this approach of using these effective terms to represent the dynamic effective. So it's just a good question from myself. Does it catch the full relativistic behavior? If you were solving the full relativistic,
yes. Yes. Yeah, it does. I think it does. So that if you have specific weird scenarios, such as decaying dark matter, there's this extra lapse thing and so on. If you just have radiation, for example, that's easy. Then yes, it really is the full thing at linear level. Yeah, but it makes sense, right? I mean, you just add in the missing gravity from the pressure and the shear and the momentum. Yeah. And apparently they exist some gauge where this is possible. You just have to find it. Yes. It looks almost identical to the synchronous gauge for the power spectrum, but the velocities are closer related to the Newtonian gauge. But that's also really what most people do without realizing is the same sort of thing. They take the synchronous power spectrum to create the densities, and then they sort of subtract 2 or whatever to get the velocities, which amounts more or less to the Newtonian longitudinal Poisson gauge. So it doesn't look very different. So in practice, you can just do this and just send spectra to people and don't say anything, and they'll say, "Oh yeah, it agrees very well." Yes.
France.
Yes.
Was wondering if wait, very nice clock.
Yes.
So, is there a limit of how many rungs do you have in your simulation? Like hard limit, or you can just have as many rungs as you?
I mean, in principle, you can have as many. You can have as many as you want. Yes, I usually go with 8 as the default, and it doesn't.
You choose it before running.
Yes. Yes. But
can it be adaptive, like?
Oh, okay. So I have 8 normally, but in practice, usually only the first 6 are actually occupied. There's like 2 rungs which are not really used. Because.
How do you choose which particles in which rung?
Right. So I ask each particle at each time step, what is your local acceleration, which is some trace of how the environment, how clustered it is. And if it's a very high acceleration, I want it to be at a high rung, meaning a low time step, so you can sort of orbit with small time steps. And then, okay, so after some time, I synchronize the system again. So now all thing is at the same time. And at this point, particles can jump between rungs, so they can reshuffle according to the new accelerations. But also, I didn't mention this, there's all these little up and down arrows. So if let's see, if this particle now, which is about to move, some way, come on. How did I skip so many slides with one click? Anyway, so let me get this. Yes, now, okay. So now this one and this one is about to move. Let's say some particle in here, due to this half a kick, gets slowed down, so decelerated. It can decide to do half a kick and join this group up here instead. But if it's accelerated to the point that it needs to go down here, it can take 2/3 of a step and drop down here instead. So every particle sort of migrates around throughout the time stepping. And I discussed it with Joachim yesterday. It's very similar to what everybody else does, but every code seems to have some slight differences in exactly how this is done. I don't think anybody knows if that's an optimal way of doing it. It hit sometimes, yes, at some bad days. Yeah, I think about it, but it seems like such a huge thing. Maybe I should dig into the FMM implementation in PKD graph and steal it. Yeah. I don't really know. So currently, I just want to I have this bispectrum stuff and the 2LBT stuff, which are both very new. Like I merged it 2 weeks ago. I want to understand this and write a paper about it. But for actual new stuff inside the code, I don't know. No. Let me take the tree. Definitely no HPH. No. Don't. I don't want to touch baryons. No. I decided that a long time ago. Okay.
All right. You can also take your questions together at any time, of course, you being a local. So let's thank you all.
I don't want to